Hello, everybody. Today we will learn equations of the lines in three-dimensional space. Before we start talking about lines, let us clarify some notation. So, what is a position vector? If we choose a point, let's say 2, 3, point 2, 3, its position vector, it's the vector 2, 3 that we can visualize as having initial point at the origin and terminal point at point P. And so I will be referring to different points by either specifying their coordinates or specifying their position vectors. Okay, so let's move to lines. You already know lines in two-dimensional space on the xy plane. Can you find the equation of the following line? Okay, so do you know what is slope? Do we know what is vertical intercept? I hope you can easily find this, and the answer should be y is equal to x plus 1. We are familiar with this already. So we will need, however, different description of the line in two-dimensional space in order to generalize it into three-dimensional space. That alternative description, instead of giving slope and a vertical intercept, will describe a line by providing any point on the line and any vector that is parallel to the line. So for example, this is the same line as in a previous example. So we can choose P naught. Any point on the line, I will choose 1, 3. It will be P naught. And a vector that is parallel to the line, we will write it here. It will be 1, 2. Please note that if you are given one point on the line and a vector parallel to it, you would be able to draw that line. It means the line is well defined. So what is equation of that line? This is equation that will involve x and y. Think of the line as infinitely many points, okay? Any point that you would choose along that line must satisfy the condition that if you make a vector P0 to P, it must be parallel to V. So P naught is a given point. Any point on the line we choose, a vector P naught P must be parallel to V. So in terms of coordinates, of the vector P naught P has x minus 1, endpoint minus initial point, y minus 3. That must be parallel to V. It means must be a constant multiple of V. I switch into column vector so it is a little bit easier to see. We can rewrite this equation as x, y. Any point on the line will have coordinate x, y such that it could be obtained from 1, 3, that initial point, P naught, plus k parameter times vector 1, 2. This is called a vector equation of a line, given a point on that line and a vector parallel to it. And this is description that we will generalize to three-dimensional space. Okay, so let's do that again. So a line, remember the line is a collection of infinitely many points, but it's well specified if we will give one point of this, P naught, and a vector parallel to it, V. Once we have those, we know those two, the line is well defined. What is the equation of the line? It's as before. Line is a set of all points x, y, z that must satisfy points x, y, z, that they must satisfy the condition that P0 to P is parallel to V. No matter which point you will choose, you will always, the vector P0, P will be parallel to V as long as P is on the line. Okay, this means that the vector here, it is P naught P, must be parallel to V. It means must be constant multiple to V. And as before, we can simply rewrite this, that x, y, z, any point on the line is equal. This is the x naught, y naught, z, what is initial points or the any given points plus parameter times ABC, a vector along the line. Okay, so this is called the vector equation. Once we have a vector equation and we write three equations separate for x's, y's, and z, we will call those parametric equations, which is the same information. There is one more form of the equation of the line, which is called symmetric equation. And if in parametric equations, we'll isolate a parameter, we have a parameter k here. We will have x from the first equation, x minus x naught divided by a. From the second, we'll have y minus y naught divided by b, z minus z naught divided by c. This is called symmetric equation. You can see that it can be written only when a, b, and c are not zero. We usually do not write that k, that parameter. That's the form, symmetric equation. So let me summarize. If we know one point, any point on the line, and any vector that is parallel to the line, we can write vector equation on it, vector equation of the line. Having that, we can easily rewrite this as parametric equations, and from that, solving for the parameter, we can write symmetric equations. Okay, so let us do some exercises. In the first exercise, we have to find a vector equation and parametric equations of the line passing through the given point. P naught is 1, 2, 3, and parallel to vector 5, 4, 5. So we have all informations we need. Okay? A line consists of all points P, x, y, z, such that equal to 1, 2, 3 plus k, 5, 4, 5. That k is a parameter. Remember, it's any real number. Parametric equations, we will write x equal 1 plus 5k, y equal 2 plus 4k, z equal 3 plus 5k. So that's a vector equation and parametric equations of that line. Can we find now 4 other points or 4 points on the line that we found in part 1. Okay, so one point we already know. I will switch to row vectors because one notation with rows because there's no space here. So 1, 2, 3 is the point on the line. We know it. But what other points are there? By changing different value for parameter, we can produce more points. So for example, when k is 1, we will produce 0.668. K can be any number, does not need to be an integer. But for simplicity, we will use maybe -1 now. If k is -1, that will give us -2, sorry, -1, -4, -2, -2. Okay? In our equation, when k is -1, we have -4, -2, -2. Maybe when k is 10, we will get 51, 42, 53. Okay, and I hope you can write a lot more, many more points. Okay, so we know how to write different points. Now, can we write any 3 vectors that are parallel to that line? One vector we already know, that's 5, 4, 5. But if we multiply that vector by 2, 10, 8, 10, that vector will have exactly the same direction, will be just twice as long. So it also will be parallel. Also vector -5, -4, -5 will be parallel to that line. That's the vector just in the opposite direction, but it will be also parallel. So of course you can write more parallel vectors. And now we'll write 2 different vector equations of the line in part 1. Means we will write another equation. X, Y, Z is equal. We need any point on the line plus k times any vector parallel to it. So instead of 1, 2, 3, we can put 6, 6, 8 plus k times, we can take a vector -5, -4, -5. This is also equation of the same line. We can also write another one, x, y, z equal any point here, any point of our choice plus parameter times a vector that is parallel to it. Maybe we take 51, 42, 53 plus k, 10, 8, 10. Okay. Those are 2 alternative vector equations of the same line. It is just to show you that that equation, vector equation, is not unique. There can be many versions of it. For the same line, you can write many equations. Maybe you can write 1 or 2 more of those equations. Okay. Another example that we will do together will be find a vector equation of the line L1, which passes through point P0 255 and is parallel to the line L2 given below. So I gave name for 2 lines. This line is L2, and we're looking for the equation for line L1. So we are looking for the x, y, z equal. We need 1 point on that line plus k or t. We can use different parameter different name of the parameter and vector parallel to it. So we have a situation when two lines are parallel, L1, L2, and we have a vector parallel to the line L1, L2. So the vector that is parallel to L2, I hope you can see it's 2, 3, 5. Okay, so the vector 2, 3, 5 is parallel to L2, and therefore it's parallel to L1. Equation of the line L1 will be then 2, 5, 5. That's the point we know the line is passing through. And the vector that is parallel, we can take the same as for the line L2, 2, 3, 5. In the next example, we will discuss equation for the x-axis, y-axis, and z-axis. Think of those axes as lines that we can write a vector equation for them. And so let's write x-axis, y-axis, and the z-axis. And each of them will be x, y, z equal a point. Okay. What is the point it passes through? Plus k times vector in the direction of the x-axis or parallel to the x-axis. What is the most easiest point? It's probably 0, 0, 0. We know that x-axis passes through 0, 0, 0, and a vector that is parallel to x-axis is 1, 0, 0. Okay. Then we will not write this anymore because it's just a 0. And that vector we recall that we called I for y-axis J, for z-axis K. So the x, y, z equation for the y-axis would be t. I will choose a different name of the parameters, 0, 1, 0, and that will be j. And z-axis x, y, z equal s times 0, 0, 1, and that's a k vector. And so we have a vector equation of x-axis, y-axis, and z-axis. The last example for this short video is find an equation, parametric equations, and a symmetric equation of the line containing the following 2 points. Okay, so we have a line with A and B points on it, and we need to write first vector equation x, y, z. For this we need a point plus k times a vector which will be parallel to it. So for the points we can take any of those two. We know it's not unique, could be A, could be B, and if we can find any other point, but we'll put A, 2, 3, 4. And what is the vector which will be parallel to that line? It will be vector AB. Okay. What is that point? 5 minus 2, 3, 5 minus 3, 2, 5 minus 4, 1. 3, 2, 1. So that's the vector equation. Parametric equations. X equal 2 plus 3k, y equal 3 plus 2k, z equal 4 plus k. And symmetric equation, if we write parameters x minus 2 over 3, y minus 3 over 2, z minus 4 over 1, that parameter will be equal, write it 4, parameter is equal all those from three different equations. We do not write this, only that part is called symmetric equation. And we have vector equation, parametric equations, and symmetric equations. We can write this, sometimes instead of writing x, y, z, we write r, okay? Position vector of the point x, y, z. It will be 2, 3, 4 plus k times 3, 2, 1. Sometimes we will write equation of the line in that form, or even 2 plus 3k, 3 plus 2k, 4 plus k. Okay, that's the end of this video. I will post the next one very soon. Thank you.